Okay, today we're going to talk about elements, molecules, and atoms. An element is a pure substance that can't be further broken down chemically or physically. A molecule is a group of two or more atoms held together by chemical bonds, and the atom is the basic particle from which all elements are made. So this is kind of in, not necessarily reverse order, that atoms can be a single element, molecules can be made up of lots of different atoms. So we're going to look at the parts of atoms next. Okay, our atoms are composed up of even smaller particles. These are subatomic particles. We have protons, neutrons, and electrons. There's others that have been recently discovered, but these are the main ones we're going to focus on today. Protons are positively charged, so P. Neutrons are neutral, so the new, meaning they have no charge, and electrons are negatively charged. What happens is the protons and the neutrons stick together to form a nucleus. Just like in our cells, we've been studying cells, the center is the nucleus, the center of the atom is the nucleus, and it's made up of protons and neutrons. Then floating around them in shells or orbitals are the electrons, and they float freely. The center is clustered together, it doesn't move. The electrons move around freely. Remember, in nature, we always talk about nature always wants to be balanced. It's always trying to seek a balance. And so in a balanced atom, an atom with no overall positive or negative charge, there's the same number of protons as electrons. So they cancel each other out, the positives and the negatives. The electrons are important because that's what gets shared in a molecule. So when two atoms come together, it's the electrons that get shared between those two things. So in some cases, one gives up an electron to another atom, or in some cases they actually share the electrons and they move freely between the two atoms. Okay, so how do we organize all these things, these elements? That takes us to this fellow. This is Dmitri Mendeleev. In 1869, he organized the periodic table of elements and also worked on some amazing facial hair. Maybe by the time this quarantine's done, my beard will rival his. But anyway, back to the periodic table. So what he found was that if he organized elements that were known at the time by their atomic mass, that certain physical and chemical properties started to get organized and they started to repeat. At his time, there were 63 known elements. Now we're up over, I think, 118. But what was really neat was that he laid them out. And he actually used like index cards to lay them out so he could play with them like a giant puzzle. He laid them out and found holes where he knew there should be elements based on the properties he was seeing, but they had not yet been discovered. So we've used the periodic table of elements some in class, but let's look at the different parts. We know it's made up of a whole bunch of squares and lots of elements. So here's just one. So one square has a giant K in the middle of it. The K is the atomic symbol. In this case, it's representing potassium. Some elements, they'll use like the first two letters of it. In other cases, it's a different symbol. So K is potassium. Up in the top left or top right corner would be the atomic number. The atomic number is the same as the number of protons in the nucleus. So potassium has 19 protons in that center cluster. Then below the name is the atomic mass. In this case, 39.098 atomic mass units. They have their own special units for measuring. And the atomic mass for an atom is essentially the weight of the protons and the neutrons. The electrons are so teeny tiny, they are practically insignificant when it comes to mass. So putting all those squares together, we have the periodic table. The periodic table is organized like a grid. there are rows going across, all the way across, and those are called periods. So we have 1 through 7. And then there's columns, and those are called groups. And the groups go up and down, and they go from 1 to 18. These things are organized because they share certain characteristics, and they're organized by their atomic number. Not the atomic mass like Mendeleev originally did, but the atomic number. It still shows us all sorts of physical and chemical characteristics. So, for example, group 1 here are the alkali metals, with the exception of hydrogen at the top. Hydrogen is kind of its own little beast. So lithium, sodium, potassium, rubidium, cesium, and barium, or iridium are alkalis. And these guys are super reactive. In fact, if you throw them in water, they will essentially explode in water. So these guys are all super reactive. On the opposite end of the spectrum, this group over here are noble gases. This is helium and neon and argon and krypton and xenon and radon. These guys don't want to react with anything. So they're characterized by their atomic mass, and it shows the groups are kind of like families. So we have metals over on this side till we get over here. We have some kind of a transition zone, a border zone here. These that are in gray in this particular one, sometimes you'll see the periodic table will have a jagged zigzag line going up. These are metalloids, which means they have some metal properties, and then they have some properties of nonmetals. These over on this side of the line are nonmetals, and then halogens and our noble gases. So let's look at our metals first. Remember, that's what I said was everything kind of this side of the line. So the first group that we talked about are the alkalis. Those are super reactive. In fact, in nature, these guys are never found on their own. They're not found as a pure element because they're so reactive, they always want to be bound with something. Next to them are the alkaline earth metals. So there's beryllium, magnesium, calcium, barium. These guys are also very reactive, not as much as the alkali metals, but the alkaline earth metals are very active and also are never found on their own in nature. These metals in here are ones that we're more familiar with, or a lot of them, from normal things we think of as being metal. So titanium is Ti, Fe is iron, cobalt, Co, nickel, Ni, copper is Cu, zinc is Zn. We have silver is Ag, gold is Au. So these are metals when we think of metals, all right? These guys are all shiny, and they're malleable, which means they can be flattened. They're ductile, which means they can be stretched out. And in all cases except for one, they are solids at room temperature. Mercury, Hg, is the only one that's a liquid. It's a liquid metal at room temperature. Now there's a few other weird metals, and they're kicked out from the grid, and they're always positioned down here at the bottom. These are our lanthanides and actinides. These are essentially, not always, but generally man-made, and they're made in big particle accelerators, okay, where they're smashing tiny little things together. So some of them are radioactive, like we have uranium down here. In fact, most of the things above uranium are radioactive. So these, because they have their own little properties, are kicked out of the center mass and moved down here, but they still qualify under the metals category. Over on this side, we talked about our metalloids, where they share some properties with the metals, and then they also share some properties with the non-metals. Okay, another important property of our metals is that they are good electrical conductors. So we look here, we have copper, that's the wiring in our house. Okay. The metalloids have that same property. They can conduct electricity. They are shiny like the metals, but they're brittle. They're not ductile and malleable. They would snap and break easily. So one that we're familiar with probably is silicon. Okay, silicon used in computer chips. So let's look at our nonmetals. Now we're on the right side of the table, and our hydrogen is also paired as a nonmetal. So the nonmetals are brittle, but they're poor conductors of heat and electricity, which is the opposite of our metalloids and our metals. They are generally solids at room temperature, except for bromine. That one's a liquid. When they're paired with either other nonmetals or with metals, they're usually gaining an electron. So when they're paired with nonmetals, they share. And then if they're paired with a metal, they're taking an electron from that metal. We talked about that pairing, which is bonding in chemistry terms. So a bond between two things. So if we look at some common examples, so let's look at water, which is H2O. So we have our hydrogen, two hydrogens. Remember, this is a nonmetal, even though it's on this side. With an oxygen, they share electrons. If we look at salt, that's NaCl, sodium chloride. Sodium's over here, that's a metal. Chloride's over here. The chloride wants the electron that sodium has, and so takes it, and that's what holds them together. They're bonded with their electrons. So some of our common nonmetals that you're going to be familiar with are carbon, nitrogen, oxygen, phosphorus, and sulfur. Okay, a lot of these guys are the basics of organic chemistry. So when we do our life sciences, we're talking about those elements for the most part. These here in the blue in this table, these are the halogens. So this is fluorine, chlorine, bromine, iodine. Okay, these are called the salt makers. And that's because they can make salt. So we have our sodium, and our chloride is our table salt. Okay, these guys are very reactive. They only need one more electron to make them happy. Okay, so they're willing to steal that electron from somebody else. So they're very reactive. These in group 18, these are our noble gases. Like I said, this is helium and neon, argon, krypton, xenon, radon. Okay, these are the gases when we think of neon signs, and they glow. You apply electricity and they glow different colors. The different colors are because there's different gases inside those tubes. Okay, these guys are noble. Think stuck up, like nobility. They don't want to deal with the commoners all over here. Okay, they want nothing to do with them. So they're happy the way they are. Their electron orbitals are full, and they don't want to bond to anybody else. They don't want a friend. They want to be by themselves. So those are the noble gases at the end. All right, let's talk about our last little guy is hydrogen. We've talked about it being a non-metal, but it's over here because it has one lonely electron. The rest of group 1 all have one lonely electron. So this poor guy wants a friend desperately and will bond to anything else that's looking for electrons. Now, hydrogen is estimated to be 90% of the atoms in the universe are hydrogen, but it's less than 1% of the mass of the Earth's crust and the oceans and the atmosphere. Okay, this is the periodic table that we have hanging in class, and you're not able to be here to see it, but what I really like about this is it shows all the different uses. So even for things that we've never heard of before, it tells us where they're used. So we have hydrogen is burning in the sun and the stars. We have our lithium batteries. We're no sodium for salt. Potassium in our fruits and vegetables. Rubidium is used for GPS, global navigation.
cesium in atomic clocks, francium for laser atom traps, radium makes our glowing hands in our watches. We have barium is used for x-rays, and strontium for fireworks, and calcium is our shells and our bones. And magnesium is used in chlorophyll, and beryllium is in emeralds. Scandium is used in bicycles. It just goes on and on of all the different uses for things. Our metals here in the green are poor metals, like tin for our plated food cans. We call them tin cans anymore. Bismuth in our fire sprinklers. Thallium is in low temperature thermometers. Polonium is anti-static brushes. Gallium is in our LEDs. Aluminum, so many things are made from aluminum anymore. We talked about carbon and nitrogen being part of our organic chemistry. Phosphorus for our bones. Germanium is another semiconductor for electronics, and notice that it's right there on the line, on the metalloid line. Arsenic is a poison. Iodine we use for disinfectant for cleaning cuts. It usually has an orange tint to it. Bromine is used in our photography film. Chlorine for our swimming pools, which hopefully will open. Fluorine in our toothpaste. We have fluoride in our toothpaste. Okay, those are our halogens. And then we have our noble gases. We have helium for our balloons, our neon signs, argon in light bulbs, and krypton in flashlights, and xenon in high intensity lamps. And then radon in surgical implants. And you can also see the little atomic symbol on a bunch of those guys. And then if we go down here to our special cases at the bottom, we have lots of things used in the medical industry for surgeries, for laser surgery, for fiber optics, fluorescent lamps. We have americanium for our smoke detectors, plutonium for our nuclear weapons. That's for Vinny and his atomic bomb questions all the time. Okay, these are our nuclear ones down here, and often the man-made ones down at the bottom. All right, so we've talked about our elements, we've talked about atoms, we've talked about molecules, we've talked about the periodic table. So I thought we'd do a little home science so that we can take a common household everyday object and split it into its two elements. So we're going to take some water. And you all tell me that's H2O, hydrogen and oxygen. We're going to break it apart, and that's electrolysis. So electrolysis is going to use electricity to break the bond holding the two hydrogens and the one oxygen together. It's going to break them apart into hydrogen gas and oxygen gas. All right, electrolysis is super easy to do. I bet you can even do it at home. There's nothing really special that's needed. You see actually all my supplies right here. So first, we need some sort of container. You can use glass container. I just used plastic Tupperware. And then we'll have wire leads. I've got alligator clips for mine to clip it to the battery. But simple wires, anything that's going to conduct electricity will work just fine. In fact, I've seen it using spoons. I'm not saying to use your mother's spoons, but I've seen it done. So the alligator clips will clip to the battery. To the positive and the negative. And then you see the wires run down in. Now I duct taped them into the bottom of the container just to help hold the leads a little easier. Coming out the other end of the clips, I have little copper wires sticking up. That's what these are. That's just to make it easier to run them up inside the test tubes, and you'll see that in just a minute. You don't have to. It would work just fine off the end of any wires at all. You also can use the graphite in a pencil. So you'll see other experiments will use graphite rods you can actually sharpen both ends of a pencil and you can run it that way instead. I found the copper wires worked well enough for what I wanted to accomplish. Then we just need some water, and I'm using distilled water so that I know that it's just hydrogen and oxygen in there. I don't have other minerals that might have been dissolved in our tap water. And then water on its own will conduct electricity, but not really well. So we add electrolytes to it. There's lots of choices. Two easy ones you probably have in the cupboard are salt and baking soda. Either one will work. Salt does have the byproduct because it's NaCl, that's sodium chloride, that when electricity runs through it, it also not only breaks up the water, but it also breaks up the salt, and it breaks it into a chloride, or makes it into a chlorine gas. So you might get the off-gassing of chlorine. Chlorine gas in itself is poisonous. At this level, it's very, very minuscule amounts. Not really something you need to be terribly concerned of, but you might notice that it smells a bit like the pool. I'm using baking soda today. So in my big beaker, I just have baking soda dissolved in water. The baking soda is acting as an electrolyte to help the conductivity of water. So, the only other thing that you might not have are test tubes. And I'm going to use those for collecting gas. The experiment will run just fine without collecting the gas, but I think it's a little more fun to see how much hydrogen and oxygen is being produced. So you can use test tubes. If you don't have test tubes, you've got other clear containers at home. They'll work just fine. The rubber bands are on here just to kind of jerry-rig a test tube clamp. And so you can see the test tube will slide down over the wire, and the rubber bands hold it in place. So that's all you need for setup. Now we'll get it ready to run. Okay, so my battery is all hooked up. You can see the leads are hooked onto the battery. You can use a 9-volt, you can use a C battery or a D battery, and just hold the wires to the ends of your battery. That'll work just fine. So I'm going to add my water in. And it's already starting to produce gas. Now the next step we need to do to collect that gas, we don't want to trap our atmospheric gases in the test tube. We want this to be just the gases that we want to collect. So what I'm going to do is fill it up in my tub. So it's all filled with the water right now. I'm going to keep it below the opening. Now that one's sitting on. I'm going to do the same side, or same with the other side. Get this one in. I'm going to put an extra rubber band on just to help hold them upright because they want to spread apart. The battery is connected now. Let's see, and it's already started generating gases. You can see them bubbling up. They're tiny little bubbles. If you look down there by the wires and by the leads, you can see the bubbles forming. They form quite rapidly. And you can see that the test tube on the right already has about twice as much gas in it as the test tube on the left. And being that water is H2O, that gives us a pretty good indication that the hydrogen is on the right, because there's twice as much gas in there as there is in the other one. So we'll let this run for a couple of minutes, and then we will test the gases. This is about 5 minutes in now. You can see the height difference between the gases. So once again, the one on the right has produced quite a bit. It's displaced a lot of water. In fact, you can see the water line in the test tube is just a little bit above the water line in the container. And the one in the left is above the green rubber band still, but you can see they're bubbling away. We'll let them run a little bit longer, and then we'll test those gases. Okay, so we've generated quite a bit of gas. In fact, the hydrogen side is down about the water level, maybe even a little below that, and the oxygen side is down a little below the green rubber band. So I'm going to go ahead and stop the reaction just by disconnecting the battery. I'll take off my little holder rubber band, and then we're going to test the gases. And one thing that we know about hydrogen is that it is flammable. So we'll get the splint lit here. All right. So we'll drain the water out, test the gas. That little pop that you heard, that's the hydrogen gas burning. Now, we'll try the same thing on the oxygen side. Oxygen won't burn like the hydrogen did, but if we get the splint going, once again, we're going to drain the water out, try to keep the oxygen inside. And nothing. Ideally, what's going to happen is that it can relight the splint with that extra oxygen layer. All right, so this is something else I read about. I don't know if it'll work or not. Or catching both gases in the same container, and we'll try to light that. Ideally, this should be the best possible flame. We'll see. All right, we'll disconnect. For the fun of it, here's some extra explosions. Do that again.